Welcome back to Preparing for Organic Chemistry. This is part 10, even more acids and bases. Just to make sure we're following our roadmap in this very large topic, acids and bases, let's just remember what our objective is. Our objective is to be able to evaluate any Bronsted-Lowry acid-base reaction, and based on the structures of the species involved, to estimate the position of the equilibrium. A related objective is to be able to look at any molecule and answer this question: which is the most acidic hydrogen in the structure? That's a related objective. Right, because if you're going to be undertaking, say, the synthesis of complex molecules, and this is a very complex molecule, then you're going to want to know as much as you can about the relationship between structure and reactivity, including structure and acidity, because acid-base reactions are just one type of reactivity mode. How are we going to accomplish our objectives? These two objectives, related objectives. We're going to understand the parameters that, the structural parameters that affect pKa, which is what we went over in the previous lecture. The other thing you're going to need to know is the approximate pKa's given a functional group. And I'm not necessarily saying memorize this table. On the other hand, in the course of learning what you need to learn, it wouldn't be a bad thing to know, for instance, that alcohols, right, have a pKa slightly higher than water. In other words, to take the structural parameters and their effect on pKa and to put some numbers on them, or put at least a range of numbers on them. Well, I promised you examples in this lesson, and that's what we're going to do. We're going to go through a number of examples. Here's the first example, and again, you are to use your growing knowledge of the parameters that affect pKa, and you're to approximate the KAB for this reaction. So go ahead and take some time and do that. Right? Make notes to yourself. Redraw the reaction in your notebook. Remember to identify, right? The first step is to identify which is the acid, which is the conjugate acid, which is the base, which is the conjugate base, and go from there. So go ahead and do that. The correct answer is that the KAB is very favorable to the right, right? And that's because the acid in this reaction is that protonated amide that you see on the reactant side, and the conjugate acid is the protonated amine that you see on the product side, right? And the protonated amide on the reactant side has a conjugate base which is stabilized by resonance and inductive effects, and the conjugate acid on the product side doesn't. So that makes the conjugate, so that makes the acid on the reactant side the much stronger acid, and therefore we go far to the right to go from a strong acid to a weak acid. Here is the next example. This is out of organometallic chemistry, main group organometallic chemistry, which has been around for a long time. It's transition metal organometallic chemistry, which is a relatively newer field, but this is main group metals, in this case lithium. All right, go ahead and do the same thing. Go through the same analysis and see what you predict. And make sure you have a reason. Okay, the correct answer is, again, this is a reaction that is far to the right, very favorable, a very large KAB much greater than 1. The acid in this equation is the terminal alkyne reactant, which you see there, and the conjugate acid is N-butane. And the acid, being a terminal alkyne, has a conjugate base that's stabilized by sp hybridization, and the conjugate acid has no such stabilization. It would be an sp3 anion, okay, which is extremely unstable. And so again, we go from a much stronger acid to a much weaker acid. Now, it may sound funny calling a hydrocarbon, right, the terminal alkyne, a strong acid. It's not a strong acid, as you learned in general chemistry, right? It's still a carbon acid, and it's a very, very weak acid. It's even much weaker than acetic acid. Okay, but relative to N-butane, yeah, it's a strong acid, and so we go far to the right. Okay, here's another one for you. Take your time. Take your time, make your notes, have a reason. This is an acid-base reaction that lies far on the left-hand side. Very, very unfavorable. How come? Because the acid in the equation is the pyridinium ion on the reactant side, okay? And the conjugate acid, of course, is the carboxylic acid on the product side. And carboxylic acids, first of all, they're called carboxylic acids. And even if you didn't know that, then the conjugate base of the compound on the product side that you see there, right, is stabilized by both resonance and the inductive effect, and possibly even the electronegative effect, right? Whereas the acid on the reactant side has none of those features, and therefore it looks like we're going from the weaker acid to the much stronger acid, and that's highly unfavorable. Let's do one more, okay? The reaction of that conjugated ketone, cyclic ketone, with hydroxide base to give the anion of the conjugated ketone and water. Where does that lie? This also is highly unfavorable, right? We have the acid, again, which is the conjugated ketone reactant. We have the conjugate acid, which is water. And now here is where it's useful to have an idea of some of these pKa's. And you will learn that the pKa of protons that are alpha to a ketone carbonyl, or to a carbonyl in general, but especially a ketone or aldehyde carbonyl, are about 20, 21, 22. Conjugation and resonance will drop that to about 19 or 20. So we estimate the pKa of the acid to be about 20. We know the pKa of water is 16. That you should know. And so again, we would be going from a weaker acid to a much stronger acid, highly unfavorable. All right, so now we're going to switch gears and we're going to do a different type of problem. Again, closely related. We're going to look at 4 molecules here, and we're going to order the acidities of those hydrogens. And by the way, when your professor gives you a problem like this, and he or she will, be very careful about the wording. Are they asking you to order the pKa's, or are they asking you to order the acidities? Because, of course, one is the inverse of the other. So do be careful about that. All right, let's see how we handle this. Go ahead and try the first one and order the acidities. That's what I'm going to ask you to do. Order the acidities from strongest to weakest acid of A, B, C, and D. Go ahead and do that. Here is your answer. The most acidic hydrogen is B, because that's a hydrogen that is stabilized by 2 carbonyls, right? And that has a pKa of around 9. You can see in my notes, I list the approximate pKa's. So that's the most acidic, followed by A. Now, A is interesting. Site A is interesting because of the double bond in the benzene ring, there is the potential for interaction with the carbonyl through that double bond through that double bond, but that's not a normal double bond. That's part of a benzene ring system, right? And it doesn't really want to serve a dual purpose. It's called bond fixation. So a normal conjugated ketone, right, would have about the same acidity at that A position as a regular alpha position to a ketone carbonyl. But because of bond fixation, it's reduced a bit, and we approximate A as instead of 20, 21, 22 at about 25. Okay? C and D are sp2 carbon hydrogen sites, but C is more acidic than D. Why? Because the anion at site C is going to involve interaction with some metal, right? In some sort of acid-base reaction, some counter ion, and that's going to be stabilized by chelation by the neighboring methoxy group. So we say that C is more acidic than D, and there's your order. B is greater than A is greater than C is greater than D. Try this one. Here's the answer. CDBA. CDBA. C is alpha-2 carbonyl and inductively stabilized by the fluorine. D is simply alpha-2 carbonyl. B is the terminal alkyne, right? And remember, alpha-2 ketone carbonyl is around 20, 21, 22. Terminal alkynes around 25. And then finally we have A. A does have some resonance stabilization, which we call propargylic. You've heard of allylic. That's the position alpha to an alkene. Well, propargylic is the position alpha to an alkyne, and there is a little stabilization, right? We go from 50 to around 45. Try this one. The answer is ADBC. ADBC. A is an alcohol, pKa of around 17, just a standard alcohol, right? A little less acidic than water. B again is alpha-2 carbonyl around 22, alpha-2 ketone carbonyl. C is allylic. C is allylic. Now C does not resonate through the carbonyl. I hope you can see that. But C has a little stabilization from the double bond in the third ring, and that's allylic stabilization. And then finally, D. D is a fully conjugated enone system, right, where the conjugate base is now fully resonated. I'm not sure that's a word, but in full resonance with that entire triene carbonyl system because of its position. So that's how we assign the approximate pKa's, and that's how we assign the ordering. Okay, here's the last one. Give this a try. Interesting molecule. All right. Let's see. This is the answer here is DBCA. DBCA. Let's see. D is a carboxylic acid, and you should be becoming familiar with that. As I mean, if you have a carboxylic acid in your structure, right, CO2H, all right, then that in all likelihood is your most acidic hydrogen, right? It's an organic compound after all. It's not an inorganic mineral acid. All right, so that's the most acidic site, followed by B, and B is resonance stabilized by that conjugated enone ketone carbonyl system, and then we have C, which is very close to B. All right, C and B are both or either resonance stabilized by that enone carbonyl ketone carbonyl system, But B is a little more acidic than C, because as you put alkyl groups on a carbon, replace hydrogens with alkyl groups, and C has one more alkyl group than B does, then that tends to, alkyl groups are electron releasing, they tend to destabilize anions. So that's the reason for C being somewhat more acidic than, that B being somewhat more acidic than C. And finally we have A, which is just simply alpha to a carbonyl. All right, so I hope that helped. This completes our introduction to acids and bases as part of the Preparing for Organic Chemistry mini course. Our next and final topic is reaction mechanism.